Okay, let's move on to the next presenter.
It's Dr.Jae from APEC Climate Center, and his talk is, the title of his talk is Climate Change Impact on Agriculture Drought by Considering Uncertainty of CMIP5.
Yeah, my name is Jae from APEC Climate Center. Today, actually, I talk about the climate change impact on agriculture drought by considering uncertainty of CMIP5 data. This talk covers actually, at first I want to talk about what is the important thing should be considered in the climate change impact assessment. Then I want to talk about the data which I use for this project. And then I want to, actually the precipitation is very important for the water resources, so I want to check the precipitation characteristic a little bit. And then finally, actually I will just talk about the assessment of the climate change impact on agriculture drought, and I will give some suggestions in climate change researches. Dr. Kim already mentioned this. Actually, I don't want to spend time here, but this presentation will cover directly from the GCM daily data to the station the data, downscaled and bias correction. And also I will just focus on the process. So I have two questions actually. How the climate change scenario reproduce the spatial and temporal pattern of the historical period, because the GCM gives the historical data. But if the data cannot reproduce the temporal and spatial pattern, actually we have to consider that kind of information in the decision actually making. So actually I brought two example. Even though we have the same future projection by 9.1 increase, and here's the two cases. For example, one is actually we have a good reproducibility of the temporal trend. And maybe we have a bad reproducibility in this case. So even though we have the future projection, we need to consider this kind of information. Maybe we can rely on the information a little bit more. So this one is for the historical period, but actually for the future period, actually we need to think about uncertainty. Some guys actually complain that actually even though actually they apply the same actually the watershed, but they get a different actual signal. One is maybe can be increased, maybe one can be decreased, and then in the case actually the decision maker can be confused. So that's a bad situation. So but even though we have the same actually the future projection, maybe we need more additional actual information for the decision making. The first case is a high uncertainty band, and the second case a low uncertainty band. Actually, that kind of information also should be to the decision maker. So let's talk about the data which I use. Actually, I collect the data, daily CMIP5 data globally, and actually we collected 33 GCMs. And one is the KMA RCM data. It's a 12.5 kilometer resolution. So about the variable, actually I consider 6 variables. And this 6 variable is necessary for the watershed modeling. Actually the model name is the SWOT. So I collect the precipitation mean max temperature and wind speed and relative humidity and solar radiation. And this shows the spatial resolution of each the GCMs, and actually that tells us actually we need some spatial downscaling. And this graph also shows some actually the stream flow simulated by the actual observed data, and one is actually as an input using the KMA 12.5 RCM data. And it shows them actually there's a big difference gap between the observed and the RCM based data. So, but here we can check that this pattern follow the precipitation pattern. So it means we have to consider the actual bias correction at least monthly. So I use the non-parametric quantile mapping method. Actually, I want to explain the concept of the non-parametric quantile mapping. This graph shows it's the original GCM data, and the black line shows the observed data, 30-year monthly mean. And actually, there is a gap within the actually month by month like this. So here, actually, for each month, we can get the PDF like this, and we can get the information based on the observed and the GCM. Actually, that's the quantile, the information. And using this information, we can actually the bias correct for each month like this, from January through December. And this information also used for the future scenario. And this graph shows the one is the it's original the scenario data for the future period time. So this quantile mapping information is used to adjust this future period times like this. So we can get the bias corrected the future scenario data. So this is the concept of the non-parametric quantile mapping. And we have a multiple station within one GCM grid, so we can do this kind of process one by one independently. So we can get the bias corrected data for the whole Korean KMA stations. So this shows the example of the not bias corrected original the GCM data for the historical period, and actually for the one specific the location in Korea, Jeonju station. And as you can see here, the black line shows the observation data, and most of the GCM cannot mimic that temporal pattern. So it means most of the GCM underestimated during the wet period time and overestimated during the winter season. So we need to collect this kind of the pattern also. Here, the maximum temperature, most of the GCM underestimated. And about the minimum temperature, some model overestimated, but some model underestimated. But relative humidity, wind speed, and solar radiation, actually, most of the model actually it overestimated compared to the observation. But here, actually, wind speed, GCM do not provide 2 meter, actually, the wind speed. So this one came from 10 meter, actually, from the surface. So using the bias correction, actually the quantile mapping method, this shows the bias corrected data for the same station for the future, actually the RCP 8.5 scenario from 2011 to 2040. So as you can see here, lots of things is collected here, but as you can see, the precipitation has a huge uncertainty during the wet period time, and within the maximum minimum temperature, most of the model shows the consistent actually trend is higher than actually historical MME. This one is the historical MME, and relative humidity and wind speed and solar radiation is very close to the historical MME. So because of the precipitation data has a huge uncertainty during the wet period time, so I just want to check the precipitation index, the characteristic of the rainfall. So I just consider 5 the precipitation index. First one is maximum the wet season, actually June through September precipitation amount, and second one is maximum daily precipitation, and third one is number of days daily precipitation is greater than 80 millimeters, and 3 index are related to the flood management, and the other 2 index are dry season precipitation and maximum number of the consecutive dry days, and these 2 index are related to drought management, something like that. Before I show the overall result, actually I want to explain a bit how we can actually analysis the graph. Actually, there's 4 columns here. The left side shows the observation, and second one is historical RCP 4.5 and 8.5, and column, actually this box plot is the the multimodal ensemble. And the remaining things here are individual models. So within the graph, actually, we can check that the two kind of things. One is the blue line and blue shading means actually we can compare to the observation. If the mean is the same, actually that the data is reproducible, and it is very good for actually mimic the actual observed data. And also we have to consider the range of the data. So here actually the observed data has some this kind of ranges, but within the climate change scenario, actually it has a higher some variation, something like that. Within the scenario, actually we can compare the red line is the reference data is the historical MME. So we can compare this model actually predict the decrease of some variable, and we can also compare the multimodal ensemble here. And also we need to check the ranges compared to the historical MME ranges, and maybe this the RCP 4.5 and 8.5 increase some actually variations. So let's see the output. Actually, in Korea, actually we have the 76 KMA station, but actually I just selected the 59 station which has more than 30-year observation data. So this shows the 4 major rivers in Korea. So I just average it for each basin. So this column is a basin, and this is scenario. Let me see the actual output. First here, the wet season precipitation, actually we can get the actually very close the mean, but here actually most of the basin shows the scenario data has a higher variations. And also here we can see the changes in the future scenario, and compared to the historical MME, actually some model under-predicted and over-predicted, but most of the actually the MME for the future scenario actually shows the orbit increase of the total precipitation from June to September. About the daily maximum precipitation, it's the same, but here we can check the reproducibility by the MME, and we can check the individual models. And here also it shows some higher variations. For the future scenario, actually it also shows some actually orbit increase of the maximum daily precipitation, and also the model shows the higher some variations like this. Number of days, the daily precipitation which is greater than 80 millimeters shows the trend. The model is reproducible, the data was reproducible, and the range is a bit can be increased. And for the future scenario, it's the same. Actually, the watershed shows the orbit increase of the number of days, which is greater than 80 millimeters, and the range can be a bit increased within the future scenarios. So based on these 3 index, actually we can consider actually in the future scenario the flood related index can be actually increased. The number of the total precipitation and the number of the maximum daily precipitation, and also some severe storm event can be increased in the future scenarios. Let's think about the drought related index. At first, actually this one is the precipitation amount from the October the next year May, and within this here graph actually we can see the orbit increase of the average the mean value here. So but most of the model shows very actually close to the observation. So the data is reproducible, but here actually compared to the flood related index, actually the range is almost the same to the observation. For the future scenario, here actually orbit increased, but the ranges is also increased like this. And maximum days is a bit the problem here. originally the observation data has the very higher value like this. But within the scenario data, there's actually very underestimate of the maximum dry day. So I think it can be explained by the characteristics of the GCM, because the GCM usually actually the rainfall event is all the day. So even though we just correct using the contour mapping, very small, the precipitation is corrected to the precipitation event, but some actually the smaller than actually the precipitation is still existing, and then the consecutive dry day is not corrected. But if we consider actually this is the threshold value as a 0 millimeter, but if we use maybe 1 millimeter, actually it can be fixed. For the future scenario, actually there's not much changes here. So based on actually this kind of information, drought related the information, actually it can be a bit some actually increased. So let's think about the agriculture, the stuff. So in Korea, there's more than 17,000 agricultural reservoir, and as you can see here, 62% of total water resources are used for agriculture, and 80% of the agricultural water are used for the paddy irrigation. And 80% of the irrigation water for paddy area are supplied from the agricultural facilities, including the reservoir. And 56% of total irrigated area are supplied the agricultural reservoir. So agricultural reservoir is one of the very important, actually, the factor in Korea. But the problem is, compared to the multi-purpose dam, actually the agriculture reservoir is very small. It means actually it's vulnerable to the climate changes. So that's the reason I'm interested in this topic. And let's think about the actual component of the agriculture reservoir. At first, we need to think about the shading area means the paddy field in this watershed. And we have to check the irrigation demands can be changed. It depends on the climate changes. So one factor is the demands, and also here's the reservoir here. But usually the water came from the upstream watershed. So we have to check how the upstream inflow can be changed depending on the climate changes. So based on these two information, we can calculate the reservoir storage level of the reservoir. So I selected 104 reservoir in Korea, and let's think about the result. So explain the reproducibility and the uncertainty of the analysis. Actually, I choose one actually representative the reservoir here, and I used the homers. Actually, this model is used by the Carico. Is the one actually the company in Korea which dealing with the agriculture water resources. So inflow is calculated by the 3-level tank model, and demands is considered by evapotranspiration, water supply for sowing, planting, and loss, and storage is calculated based on water balance. So let's think about the reproducibility of the irrigation demand. This shows the black line is the observed, and the red line is a multimodal ensemble. And as you can see here, the data shows that actually it mimics the temporal trend. So the bias correct data is appropriate for this purpose. But as I mentioned, actually the bias correction is conducted for the monthly. So I want to check the smaller time step. So I also check the 10-day time step. So here in monthly, the biggest difference is 10.5%, and also the smallest R square is 0.97. And I checked the 10 days, the trend also, it was okay. Actually, it mimicked that the temporal trend. So the data is, even though we do some actually bias correction based on monthly, actually 10 days, the temporal trend is also okay. So here, as you can see, the smallest R square value and the largest R square value is within these ranges. And as you can see here, the MME usually hides the R square value. So it means actually, instead of using one model, actually it will be better to use the multi-model ensemble to get the temporal some reproducibility and the uncertainty, something like that. For the monthly inflow, actually the inflow is better than the demand. So you can see the black line and the red line is almost same. And here, as you can see, the difference is 2.2%, and it's almost 1, the R square value. So 10 days, actually the trend shows that very close each other. And here, actually this model is a bit bad, but it's within the good ranges. The storage level is also same. Actually, the smallest, the largest difference is minus 3.6, and the lowest R square value is 0.74. The 10 days also is acceptable. So this is based on the one actually representative reservoir, but let's think about the future uncertainty. Actually, this shows the uncertainty bound the bands here. So as you can see here, we can get compared to the multimodal ensemble, the range is minus 11.2 to the 11 points. So that kind of information is very useful for decision making. And also for the inflow, it's the same. It's about minus 11 point to 11 point. And for the storage, the actually uncertainty bound is decreased, because if there is a big rainfall, actually most of the water actually fills the reservoir and goes to the stream. So it's not sensitive to that kind of the climate change scenario. So let's think about the whole 104 reservoir. Actually, I want to give some decision makers some information based on the group, some cluster actually of the reservoir. So I do some cluster analysis, and it gives the 5 different group of reservoir. And actually, it shows that each group of the reservoir shows a very similar trend, and this is the uncertainty bound for each group of the reservoir. So actually, the inflow, the demand is increased for most of the reservoir cluster, and the inflow also increased a lot, and the storage level ratio actually is increased a bit. And based on this kind of storage level, actually, I calculate the agriculture drought index from the reservoir. And this one is if this 10-year frequency, actually, if the index is less than minus 3.3, actually is a severe drought. So I just calculate the number of the count, which is below that kind of index. And this shows the actually index. And the result shows the 2, 3, 4, 5 actually group actually shows the drought will be the worsen, and 1 is a bit decreased. So this is my conclusion. Actually, I don't want to tell the exact the impact of the climate change on the agriculture reservoir in Korea. More than I want to talk about, actually, we need to consider actually that kind of information will be very important. Precipitation shows the higher uncertainty, and reproducibility related information for the downscaling bias correction should be provided, and multimodal ensemble is necessary in order to consider uncertainty. And this is what I want to talk to this group. Actually, within this video, actually, here's the climate change data provider, and this is the end user. And we may have several actually downscaling the scale tools, but actually we cannot, actually the evaluation of this the tool approaches and data we cannot do by ourselves. Actually, every application has a different purpose, and it means the application has a different actually major process. So it means we have to consider that kind of process, and then based on that kind of process, we have to evaluate which one is better to reproduce that kind of characteristic, and then based on that information, we also have to actually give some idea which one is better to consider that kind of thing. So that's the reason we are just actually get together here to share some actually the idea and comment and evaluation actually information about in this kind of framework. So concerning the future about the downscaling, actually we need to consider spatial variable coherence, and maybe hourly data is important for some purpose, and also we need to generate some grid-based data. So next the step is about the downscaling for this area. Thank you very much.
We have time for a few quick questions. Are there any questions from the floor? First, I'd like to ask a quick question. You developed one agricultural drought index. Could you give details how that index was derived? Can you explain that?
Actually, we just get the storage level for each 10 days, and then we just get the density distribution, and then from that the product density distribution actually I can convert to the some indexing like that, the normalized indexing like that. But yeah, I cannot detail. I cannot explain in detail here. So like that.
Correct.
Yeah.
Any other question?
Just curious that do the APCC also have the seasonal forecast model and product? So are you applying the similar concept to make a seasonal forecast?
Yeah, yeah. Actually, last year, actually, this was my personal research topic, but this year, lots of the researchers in APCC are focusing on the how we can use that seasonal forecasting from APCC. And so this year we can dealing with that kind of downscaling issue and bias correction issue. Yeah, actually, maybe the approach can be different because the original crime data is different. The APCC MME is a monthly data. So maybe actually we have to dig out that kind of approach, and then maybe next year I can provide some information based on that kind of research, something like that.
I think because of the time constraint, if you have any other question, you can wait until the discussion session.